Thank you. I'm happy to be here. I have, as was just said, I'm going to talk about quasars at a variety of redshifts, and we'll try to tell you about quasars in general with SDSS, and then some specific things on the clustering, something about obscured quasars, what we can learn about black hole masses. I will probably run out of time about here, but if I have more time, we'll find myself talking about the very highest redshift quasars and what we can learn about them there. And I understand that Xiaohui Fan was through here about a year ago, and there's probably not much that he didn't already tell you about that's there, so you won't miss too much. So this is work that I've been doing with a large number of people, and this is the necessary slide to list all my many collaborators, and the ones in red are the ones working closest to the work that I'll be talking about now, and I'll mention in particular Yue Shen, who's a graduate student with me now. Actually, this was a small semester project on the side, which has blossomed into enormous things, and he's in fact doing a thesis on extrasolar planets. So we'll see what he does in his spare time. You'll see it's rather impressive. So why are quasars interesting? It used to be when I was a graduate student that AGN were sort of I remember my thesis advisor saying, "Why are you interested in AGN? They're sort of like butterfly collecting, right? You know, they're pretty and they're interesting and all, but it's not really telling you anything really deep about what galaxies are, which is what we really care about, or cosmology or other things." But in the last years, we have come to realize that the story of galaxy evolution, the story of quasar evolution, are tightly coupled subjects. And part of the reason is this plot, or similar plots that have been published, showing that there is a very tight relationship between the properties of the host galaxy of quasars, in this case, the velocity dispersion of the bulge of nearby galaxies, and the black holes, the mass of the black holes in which they sit. And the qualitative statement is that essentially every large galaxy hosts a supermassive black hole in its center. And once one realizes that, one realizes that the process of black hole growth, which is what we call the quasar phenomenon, and all the associated questions really are an important part of understanding how galaxies themselves evolve. And so this is basically an explanation of why we all should care about AGN. They're really not just a strange thing that a rare class of galaxies do on occasion, but they really seem to be part and parcel of the whole story of galaxy evolution. So the tool that I'll be using is the Sloan Digital Sky Survey, and it involves a large number of institutions there. And here are the stated goals, which we're actually very close to finishing. We're using a dedicated telescope, this one here, to survey the high galactic latitude sky in the north with 5 photometric bands over about 10,000 square degrees, spectroscopic survey of 1 million galaxies and about 100,000 quasars to study their properties, and a huge emphasis throughout on really getting not just large quantities of data, but very precise data, very accurate photometric, spectrophotometric, and astrometric calibration throughout. So this is already an out-of-date slide, but gives them some sense of how far the SDSS is. This is actually the so-called 6th data release, the data taken through summer 2006. We just about finished our contiguous area in the northern galactic hemisphere that one sees here. As you can see, it was just about finished even back then. And this was the spectroscopic coverage back then. I really do need to remake this plot. And we're within about, we're actually within a few weeks of finishing off this entire survey. And this will appear a uniform gray over this entire region with spectroscopy. So even back then we had, well, in this picture, 9,600 square degrees of imaging and about 1.3 million spectra. That number is, I think when we're all said and done, it's going to be close to 2 million spectra, which is an impressive number. We said 1 million when we started out, so we got 2 million. I don't think anyone's going to be too upset about that. And just to give a sense of the depth, the imaging data going down to about 22.5 in R, and well, we'll have more to say about the spectra in just a bit. So what is it about SDSS that makes it good for studying AGN? Well, as I said, we have 5-band photometry, very uniformly calibrated over about 10,000 square degrees, just a shade under 10,000 square degrees. And as we'll see in just a bit, the photometric system is really optimal for separating quasars, which appear point-like, and stars, which of course are much, much more common. And we'll see how that separation happens in just a bit. We have hundreds of thousands of high-quality photometrically calibrated spectra of galaxies, which we can go do AGN studies on. And we'll have a little bit to say about that in this talk. You can ask me more about that if you're interested. And then the quasars themselves uniformly selected. The numbers are indeed, I think with the latest numbers, we're just about at that 100,000, which was our goal, at all redshifts. And we'll see what all redshifts mean in a bit with really high-quality spectrum. So let's get a sense of how that works. We have this filter system that I've already made reference to. The filters have the name U, G, R, I, and Z, covering the optical spectrum from 3,000 angstroms where the atmosphere cuts off, up to 10,000 angstroms where silicon is no longer sensitive. And what I've superposed in this picture on top of the filter curves is the spectrum of a normal quasar, which is with its very blue continuum. And what one sees here with the very blue continuum is that the relative flux in the U and the G bands, these objects will have a very blue U minus G color, similarly very blue G minus R, R minus I, and R minus Z color. And so what that means is that when we make a diagram like this one, where we compare the colors in the U and G filters on the x-axis and the color in the G and R filters, we can see where quasars lie relative to other stellar objects. What's plotted here are the distribution of unresolved objects in the Sloan data. Now, ordinary stars are our nemesis in this case. They're of course much more numerous in a flux limited sample than are the quasars, and they form a basic one-dimensional sequence based on their surface temperatures. The coolest M dwarfs will be in this region of the diagram relatively red in U minus G, G minus R, and as temperature goes up, they go significantly bluer, but they take a jog here because A stars, from F to A stars, there's a strong Balmer break such that the colors no longer become bluer in U minus G. There's a suppression of the U band light while the G minus R color does get bluer. So the A stars end up here, and then the very rare, very hot O and B stars, most of which are in fact are white dwarfs at the magnitudes we're looking at, end up down here. The quasars, again, don't have that break, and so appear just in more or less the continuation of this diagram in this region of the diagram. And so selecting out quasars, at least at low redshift below about 2.2, is simply drawing this diagram and drawing a box around here. It's not exactly what we do, but for the purposes of the present discussion, that's just fine. Okay? So what happens is we go to higher redshift. Here's a quasar at redshift 3.5. And again, the filters, and what you see now is that there is a break that shows up in the quasar spectra. Blueward of the Lyman alpha emission line, there's Lyman alpha, you have absorption from the intergalactic medium, the Lyman alpha forest, that systematically suppresses the light in the U and G band. In fact, the first thing that happens is that the U band light is suppressed, and so the U minus G color is no longer as blue as it was before. And so going back to this diagram, what happens is that a quasar that was in this region of this diagram becomes systematically redder in this U minus G color because the U band flux is getting absorbed by that Lyman alpha forest and moves systematically over here. And so by the time you get up to redshift 3, the quasar lives in this region of the diagram, which again is a very clean region. There's very few objects. You can see at a glance that quasars at redshifts above 3 are pretty rare. You don't see a whole lot of dots here. Lots of low redshift quasars. Higher redshift quasars are fairly rare. You can see that. Again, the G minus R color doesn't change very much because in those filters you still see that power law blue continuum. The Lyman alpha forest doesn't hit there. By redshift 3.5, again, now the Lyman alpha forest is in the G band, and interesting further things are going to happen. Indeed, what basically happens is we lose the U band altogether, and this diagram, which required detections in U, G, and R, no longer becomes useful. But we have other filters, and so we can keep on going. Here we make another one of these diagrams, G minus R on the x-axis, R minus I, because remember we have an I and Z filter as well. And now again the stellar locus looks like that. In this diagram it turns out that quasars and hot stars are degenerate. They're basically all the A and F stars plus all the quasars live in this blob around here. But the higher redshift quasars now are going to be relatively red in G minus R. Again, we saw that back here. The G band has got the Lyman alpha forest right in it. And so while the R minus I will still be relatively blue, and so the higher redshift quasars will live in this region of diagram. Again, you can see those things are fairly rare, but it's pretty straightforward to go and measure them. It's all well and good. That will continue until eventually the absorption from the Lyman alpha forest and the Lyman limits actually eventually knock out the G-band as well. And then you have to go to the next one of these diagrams. And we can see that here, redshift 4.75, the U-band's gone, the G-band's just about gone. The R-band is now suppressed, although not completely gone. R minus I will be red, I minus Z will be blue. We can make the next one of these diagrams, and it looks like this. R minus I on the x-axis, I minus Z on the y-axis. The stars, again, are this locus, and the highest redshift quasars live in this region. And so that is basically the technique that we have used to go find the highest, find quasars at all redshifts, again, from 0 up to, this will take us up to a little bit over redshift of 5. And again, going beyond that will be, if I have any time, which I doubt at the end of the talk, I may come back to pushing beyond that. But this basic technique will take us up to about redshift 5. Pat, I think our record is 5.4 using this game alone. And further games have to be played to go to higher redshift yet. Okay, so what do we get out of this? Well, here are just example spectra of quasars from redshifts, in this case 0.04 all the way up to redshift 5. And you can see the various emission lines march on in a beautiful sequence all the way across. And what's shown here, just look at the solid histogram for the time being, the histogram of the redshifts of these objects. And what one finds at a glance is you see that the low redshift quasars are indeed much more common in a flux-limited sample than in high redshift quasars. And you can see some structure in the dips in there. There are regions of redshift space where it turns out that the selection of these quasars becomes a little less efficient. And these dips are not real, but are rather due to selection efficiency that didn't stop certain strange people to write papers about periodic redshifts and other weird things. But we will not talk about that here. Okay. Okay, so here's another beautiful way to do this. Shall we put this diagram together? You just stack the spectra of all these quasars. That is, each horizontal slice across this is a spectrum of one quasar in increasing redshift order. And what one sees as a given emission line marches up in redshift, it makes a swath across here. The slope is just the relative number density of quasars. And here's the most reduced data I've ever seen, almost 50,000 spectra all into a single PowerPoint plot. So I thought this is a very pretty way to look at one's data. Okay, so given all these data, then there's a whole lot of things to do. And I want to tell you, to start with, about some of the things that clustering of these quasars can tell us. So let's start that discussion. So the scientific question here is, how is the clustering of quasars change with redshift? And we first want to remind ourselves why that is an interesting question. We look at the cosmic microwave background. We see these incredibly subtle fluctuations at the level of 1 part in 10 to the 5th. We look at the present-day universe. Here's a pie diagram of the large-scale structure as measured by SDSS galaxies. We see this tremendous amount of highly structured universe. And we want to ask the question, how is it that the universe made the transition from almost perfectly smooth to this very clustered state today? And of course, the theorists have great fun simulating this in great detail. But as observers, what we'd love to do, and the theorists tell us a story about gravitational instability and these overdensities collapse under gravity and all kinds of wonderful things happen. But as an observer, we want to see that happen. We have because of the finite speed of light, we have the ability, by looking at high redshift, to look back in time. And so we can actually see what the universe was like at some intermediate time between these two snapshots and ask, how was the universe clustered at that intermediate time? So that, and quasars, again, are that probe that will allow us to ask what the universe was like in those early days. So the prediction would be, well, it was very smooth at the distant past. It's very clustered now. So in between, it must be something in between. It's not, you would expect naively that at some intermediate redshift, the universe will be less clustered than it is today. So that's the first naive thought that we might have. But that turns out not to be the case. Galaxies at high redshift are known to be very strongly clustered. And this is a picture, in this particular case, from the Deep 2 survey at about a redshift of 1 from Coyle et al. And I think there must be better pictures of this now. This is from one of their early papers. But what one sees at redshift of 1 is the same rather intricate structure of clusters and voids and filaments that one finds at low redshift. You find at redshift of 1. And indeed, and at higher redshifts, as well. And in fact, here's the statement: the comoving clustering length of luminous galaxies. The clustering length in this context means the scale on which the 2-point correlation function is about unity, or very roughly speaking, the scale on which the density fluctuations of galaxies within an 8 megaparsec sphere is about unity. That scale is almost independent of redshift in comoving coordinates, at least to redshift 4, about as far as it has been moved for L star-like galaxies. And so the statement is, even though the dark matter must have grown, all the theorists tell us quite convincingly, gravitational instability is probably right, and therefore the dark matter clustering strength has, the theorists are all laughing when I said that. Maybe they know something we don't. Us poor observers, we just take them at face value, and they could be just making this all up as far as we know. Okay, we won't go there. So the dark matter, as best we understand, has gone through a dramatic evolution. As you go up to redshifts 4, really should be quite a bit less strongly clustered than it is today. If the galaxies are not showing any differences, this suggests that the distribution of galaxies is becoming increasingly biased relative to the dark matter at high redshift. And bias here is a technical piece of jargon, and it refers to the fact that the clustering of the galaxies and clustering of the dark matter need not be the same. The clustering of the galaxies is going to be more strongly clustered because it represents sort of special places in the underlying dark matter density field. Okay, so we'll keep that in the back of our minds for galaxies. I'm sorry, Neil, do you have a question?
That's the present day also are using for all redshifts?
Yeah, I mean, this is, I use the word roughly advisedly here. We're astronomers, so we're the usual factor of 2 slop here. But yes, if you look at what the comoving correlation length of, for instance, Lyman break galaxies at redshift of 3 and redshift of 4 that people have used, I mean, the numbers are still about 5 megaparsecs for the comoving correlation length, something like that. Okay, so what about quasars? I was telling you about galaxies. What about quasars? Well, we know that quasars are powered by the supermassive black holes and cores of ordinary massive galaxies. And I'd like to show this picture, images from HST of the host galaxies of quasars. There were still some holdouts who were saying, well, quasars really are not a galaxy phenomenon, but pictures like this sort of make it unambiguous. Quasars live in galaxies. I think this is now completely without doubt. So if quasars live in otherwise ordinary galaxies, maybe ones that are undergoing merging that stimulate the quasar phenomenon, we might expect that the clustering of quasars should be really similar to that of luminous galaxies at the same redshift. That might be something, sort of a first naive assumption that one might make. And so maybe the quasar clustering should be really similar to that of galaxies at the same redshift. And indeed, for people have looked at the clustering of quasars up to about redshift 3 or so, and found this in very rough terms to be true. So this has been done by the 2DF team. The SDSS team has been a little slow in publishing the results, so these are as yet unpublished results. We'll get it out in the next few months, I think. But the clustering, comoving, what we're looking at here is the strength of the observed correlation function of quasars in different redshift slices. This is centered about redshift 0.5, going up to centered at about redshift 2.3. And you find that the correlation length in comoving coordinates is about the same at all redshifts. Again, similar to what one finds for galaxies. It turns out that there's actually a pretty weak luminosity dependence of the. It's not completely zero, but again, I'm waving my hand and using the word roughly the same. I'm going to go within a factor of 2. The comoving correlation length doesn't change that much with redshift or luminosity up to about redshift of 2.8. You can phrase this in terms of the effective bias as a function of redshift. See, the error bars are quite large. Again, just as I said for galaxies, the effective bias does have to grow with redshift in order for the comoving correlation length to turn out to be about the same. But let's ask ourselves, well, what happens at higher redshift? It's worth reminding ourselves, by the way, why those analyses stopped at redshift 2.8. Those are the redshifts at which the bulk of the quasars in the flux-limited samples exist. Again, you remember that histogram showed that most of the quasars in the sample are redshifts below about 2.8 or something like that. And those are the easiest to select. Those are the objects that stand in the UV excess surveys, which is what a large fraction of the quasar surveys that had been done prior to the SDSS. had been carried out. Okay, but let's ask what happens at higher redshift. Well, as we go to higher redshift quasars, we're really looking at the very tip of the luminosity function, the very most luminous objects, and therefore these are objects that are going to be powered by the most massive black holes. Okay, so here's a series of hypothetical logical steps that we're going to find ourselves testing. If, and that's a big if, the very large, very massive black holes are associated with very massive dark matter halos. Suppose that's true. That's a big step, big logical step, but let's imagine it might be true. Then those high redshift quasars should live in very rare, very many sigma peaks in the otherwise rather unclustered density field, right? Because the density field at those early redshifts has not had very much time to cluster. It's less strongly clustered than it is today. And so to get a very massive dark matter halo is a really very rare thing. And it's a shame Dick Bond isn't here, but as he showed, must be 20 years ago, rare peaks are very strongly biased relative to the overall density field. And so we expect, so if this logical flow is true, then we expect very high redshift quasars to be, in fact, even more strongly clustered than our ordinary galaxies. So let's go out and test that. Let's go explore the properties of the highest redshift quasars. Well, high redshift quasars are pretty rare, but we have a big survey, and we have more high redshift quasars than anybody. I think that remains true. And here's the statistics. The sample that we had when we did this analysis, U.S. Shen, whose name I mentioned before, led this analysis. We looked at 4,000 square degrees of spectroscopic data. Above redshift 2.9, which is what our threshold was, we had 4,400 quasars, and here's the redshift histogram going from, again, redshift 2.9 and a tail going out to redshift 5.4. These are the uniformly selected quasars from SDSS as of the time that we did the analysis. Okay. So the first thing that we can do is measure the Quasar correlation function in redshift space. And I put redshift in quotes, and the reason is because what is it that one measures? One measures a redshift. Given a redshift, one puts an object at a comoving distance using one's favorite cosmology. And here's the correlation function. Notice the scale here. These in megaparsecs have gone out to 2 gigaparsecs. And the first thing to say is that on really large scales, just absurdly large scales, this is 0 at the level of our ability to measure. And it was important to show this because there are silly papers going back forever saying we see correlations on ridiculously number of gigaparsec scales. No, I don't think so. It really is uniform. Maybe this better way to say this is we're pretty sure that the sample itself is uniform. That's a reassuring thing to say. But some things are happening down on small scales, and that's what we want to go explore. Okay. No, this is just plain old, again, redshift space, not really, because I took redshift and turned that directly into comoving distance. But yes. Yeah. So the context of Nyayesh's question is that good enough? And the answer is no. There are 2 reasons. One is that, remember that redshift is due to both the expansion of the universe, but also peculiar velocities. But actually more important in this context is the fact that quasar redshifts are difficult to measure accurately. Quasars have broad emission lines, which are often interestingly asymmetric, and defining exactly what the systemic redshift of any given quasar is quite difficult. So there's a noise in the estimate of quasar redshifts, which is much larger than the peculiar velocity effect, at the level of 0.01 or 0.02. And if we don't worry about that, we'll actually get quite seriously systematic errors. So there's a standard technique for handling that. One measures the correlation function for any given pair of objects. One measures the correlations not as just as a function of their separation in redshift space, but one divides that up into a component transverse to the line of sight and along the line of sight. And the along the line of sight piece of that is the piece that's affected by all these redshift errors. And you can project that out. This is actually, it was a pretty graphic, and they chose rather lurid colors, so I put it up here. You can plot up from the 2DF galaxy redshift survey. The same effect happens with galaxies, of course, and you can plot up the correlations in a two-dimensional sense, both as a function of transverse to the line of sight and along the line of sight. And those peculiar velocities, and in our case, because of redshift errors, you get an elongation along the along the one axis, which one then can project out. So that's the game that one plays in this game. Anyway, so here's the result when you do this for quasars. And remember again that the reason that we're able to do this exercise is because we have 4,400 quasars or something. I think that was the number. That is we need a large number because quasars are very, very sparse. There's about one of these. The number density is about 10 to the minus 7 per cubic megaparsec. That's a small number. And so one doesn't get a lot of pairs with any separation, no matter how strong the clustering is, unless you have an enormous raw numbers of objects, which is what we have here. OK, so this is the correlation function again, or it's the projected correlation function, so one has to do a little bit of arithmetic to turn it into the 3-point correlation function. But if one does the standard game, which is to model this as a power law, which is what one finds for galaxies, you find that this is actually well fit by a power law with the slope of about -2, which is very similar to what one finds for galaxies. Certainly, the standard number for galaxies is -1.8, and that's certainly within the error bars. But look at the correlation length, 15 megaparsecs. Remember, normal galaxies are about 5 megaparsecs at 0 redshift, and my statement is that number is very roughly independent of redshift up to at least redshifts of 4 or so. The dark matter underneath is less strongly clustered than that, or so we might think. So you can phrase this in terms of an effective bias for the sample. It's about a bias of 10. That is, what does that mean? That means that the quasars are 10 times, have a density contrast 10 times stronger than that of the underlying dark matter. Well, that is well, you can see the scales over which we've measured. It's from 10 to a little over 100 megaparsecs comoving, and that is a result of fitting a single power law to that. So. Right. So in order to come up with this bias number, we tried to sort of mix and match as best we can. We'll actually see that, and we'll see it in just a bit. You'll see it. So clustering was larger in the past, and in fact we can do more than that. We split up the sample into 2 subsamples, basically splitting by number from redshifts 2.9 to 3.5. The numbers of quasars in our samples dropping dramatically with higher redshift. We go from 3.5 to about 5, and for the subsample up to here, again, the bias is about 10. For the higher redshift subsample, the comoving correlation length is about 24 megaparsecs. It's becoming a seriously big number. Again, compared to 5, the effective bias is about 15 for that larger sample.
Have you made a luminosity cut?
Yes, next plot. Next slide. Actually, there. One plot ahead. Let me answer that right away. Yes, there is a luminosity dependence, so let's see what's going on here. The black points are all the quasars between redshift 2.9 and 3.5. The blue points are that subsample of the highest luminosity. Turns out an absolute magnitude of less than -27. And you can see that there is a luminosity dependence. At lower redshift, one doesn't find a dependence of the quasar clustering on luminosity, but at these highest luminosities, one does. We don't have we're pushing our limits in terms of statistics here, and we can't slice and dice our survey too finely to go explore that. But yes, there is definitely a luminosity dependence. And in fact, very roughly speaking, it seems that if you cut at the same luminosity, our 2 redshift bins are roughly the same within the rather substantial error bars that we have. So, but here's another way to graph it. Again, the comoving correlation length as a function of redshift, various measurements at low redshift with their individual error bars. And indeed, it turns out that the green points are the so-called good fields, the ones that we think that are the most uniformly selected. And so you can see that the comoving correlation length is growing. And as your question implied, it is a combination of both redshift dependent effects, and certainly within this highest redshift bins, there is a strong luminosity dependence as well. Okay. So what does that mean? That's kind of cool. And indeed, remember, we went through this rather elaborate logical series of steps to come to the prediction that maybe these things were strongly clustered. We said these are high luminosity, and therefore we might imagine these are large black hole masses. And if they're black hole masses, we might imagine they live in very massive halos. And if they're massive halos, and we believe the whole cold dark matter scenario, we might imagine that these things are very strongly clustered or very strongly biased. That was the series of logical, rickety ladder of logical steps I'd taken you through. But observationally, lo and behold, it actually seems to work. So we're happy. OK, so let's see if we can understand that a little bit more. Suppose it's true that quasars are found only in dark matter halos above some threshold. It was sometimes called threshold bias in the jargon of this thing. The higher the threshold, the more strongly the halos would be biased. The rarer those halos become, and the more strongly they become biased. And therefore, measuring the clusters in the context of this model where quasars live only above some threshold tells us what that minimum mass of that threshold mass might actually be. Okay, so that's one thing we can do. Moreover, again, if the higher one goes up in that threshold, the rarer these quasars become. And I should say it more carefully. The rarer the halos become, but we have the observed number density of the quasars. So are those two numbers likely to be the same? Well, the answer is no, because a quasar need not be on for the entire time the halo's around. In fact, we think that a quasar is shining brightly for only a fraction of the time. The black hole is always there, but it's actually going to be shining for only a fraction of the time. And so if we can compare the expected number density of these halos and the observed quasar density, we can ask the question, what is that fraction of the time the quasar is shining? And that's a hot question in the field these days. People would love to know what the duty cycle of quasars is, or equivalently what their lifetimes are. So these are the kind of things that we can try to play with. So someone asked for, they wanted to see, as it were, data and model. Imagine that all quasars live in halos with masses about 2 times 10 to the 12 solar masses. What this plot shows, it's a little movie of, in different redshift slices, you saw the redshift going by, for halos at a constant mass threshold, what's happening to the dark matter? You see the black curve goes down. The dark matter at different redshifts, as you go to higher redshift, becomes ever less clustered. But the subset of the halos at the high mass end become ever more clustered, and the effective bias goes up and up. If we could go all the way to redshift 6, that would be cool. Again, I'll run out of time long before I get to talk about redshift 6 quasars. We have found them. We don't have nearly enough to play clustering games. It would be way cool, but we're not there yet. Well, so this is what the dark matter correlation function does. And notice that this particular plot is centered at 10 megaparsecs. In fact, most of our data is further out. Remember that what we're actually measuring is, first of all, a projected correlation function. So that will wash out some of the interesting effects in the shape of the correlation function. And well, look at our error bars. So and our bin sizes. I don't think we're sensitive to very subtle features in the shape of things here. So all we did was fit a power law. I wish our data would allow us to do more of that, but we wouldn't dare go further than that. Okay, so here are the numbers. If you put it in terms of the threshold mass, the halos that we're talking about are several times 10 to the 12 solar masses. We used 2 times 10 to the 12 in that diagram that we just showed. And after all this is actually not a terribly surprising number, because when one goes through, in fact, similar arguments at lower redshift, this is the kind of numbers that one comes up for lower redshift quasars as well, or very massive black holes in the present-day universe. Okay, so after all of this, in one sense, our result is very surprising. 25 megaparsec comoving length is clustering length is just a huge number. On the second hand, in retrospect, that's not very different from what we would have expected through this whole argument. This threshold mass is the kind of numbers one might have guessed a priori based on number. It's not completely out of the question. We talked about the higher at higher redshift, the higher luminosity quasars, maybe even a somewhat higher halo masses. And when you try to go through the quasar lifetime argument, after one propagates through all the error bars, the uncertainty is at best you can make a factor of 10 statement, which is that the lifetimes are in the range from a few to a few tens of millions of years, which is again the order of magnitude of the kind of numbers that one might have expected based on arguments at lower redshift. This argument is, given the errors on everything that we've measured, both some of the theoretical errors on exactly what the relationship between bias and clustering and so on might be, and the observational errors on the comoving correlation length. We really can't make much more of a precise statement than this rather woofly one here. Okay. So I should give a nod to the CFA group who have been trying to model the clustering of quasars. And they have an elaborate model. And maybe I think you have had some recent talks on this where they say that quasars go through a series of phases. They're basically triggered by mergers of massive galaxies, and their luminosities of an individual one of these mergers changes dramatically as a function of time as the merger continues and dust comes in and out. And the most luminous quasars in their model are going to be close to the Eddington limit. That is, they're accreting at close to the maximum rate their black hole mass might be able to give. In that case, the black hole mass is proportional to luminosity. While at the lower luminosity objects, there would be a range of different Eddington ratios. And so the clustering properties of quasars are different for the highest luminosity quasars and the lower luminosity quasars. And that's part of the context of the argument that we made, that the higher redshift quasars may really be different from the lower redshift ones that we have. Okay. Do I have until 4 or 4:10 as I continue? What is the standard here?
No hard limit.
Okay. So you guys just shut me up if I drag on too long. Okay. So another context of that prediction is that if we were to push to lower luminosities, eventually the comoving correlation length should actually go down. If we go to lower luminosities, lower black hole masses, we should find that the clustering strength should go down. Here is a plot from a paper by Hopkins et al. Comoving correlation length as a function of redshift. Here they've plotted a variety of different measurements from low redshift quasars and put on a model that, again, at redshift 3 takes off. They published this before we had published our results. Here are 2 measurements, and it's actually astonishingly good. They set this magnitude limit. This was for a flux limited sample. They set their magnitude limit based on what they knew we were doing. We did talk to each other, but I told them, I didn't give them numbers beforehand. Off it goes. If one had enough quasars at a brighter magnitude and therefore more luminous quasars, this is what they predict. We don't have enough quasars going a full magnitude brighter to be able to see this, and presumably at lower luminosity, they would predict a curve that is systematically lower, and that would be wonderful to go probe. Okay, I'm going to skip some of this stuff, and what I want to talk about is small scales. And what you saw there in the correlations that I showed was, you may remember, the plot started at 10 megaparsecs and went on from there. But one wants to know what's happening on small scales. These days, it's very popular to talk about models of halo occupation, where one imagines that individual dark matter halos might host more than one galaxy in the usual language. An individual halo may have a scale of something like 1 megaparsec. And if you want to go find out what's happening inside a halo, you got to go measure correlations on smaller scales. So this is a particularly pretty plot from Ouchi et al. Looking at the correlation function, in this case of redshift 4 galaxies, which is a beautiful power law. This is angular correlations, but you can same thing. Beautiful power law, and then on smaller scales, you see a deviation from the power law, and that's interpreted to be due to multiple objects within a given halo. So do quasars do the same thing? So this is work that Joe Hanawi, now at Berkeley, and I did part of his PhD thesis. And the idea was to look again in the SDSS and see if we could find close pairs of quasars to go find out what the clustering of those objects may be. So here's the game. Turns out that SDSS by itself doesn't do this very well because there's a limit on how closely 2 spectroscopic fibers can be placed next to each other. And so there's a systematic bias in the SDSS data themselves against close pairs of quasars. So we have to go out and do our own measurements. So here's the game. We take a quasar who's spectroscopically confirmed in SDSS. There it is, this little blue object. And what's shown here is where that particular object lies in color space. The same kind of diagrams that I've shown before. You look around it and notice that this object, that object has the same colors as this object. So here's the zoom in of those same color diagrams. The first object in color space, the second object. You see they're actually quite close to each other. 2 objects of similar color, in close proximity to each other, you say, well, maybe this is a physical binary quasar pair. And so you go out, and we spent a lot of time taking spectra of those other objects that we find. And lo and behold, the two quasars are at the same redshift. Here are the two spectra. And you see the emission lines all line up. This is not a gravitational lens. In fact, some of this was, the other thing we were looking for was gravitational lenses. That's another cool story, which we will not get into. But you can see that it's not a gravitational lens. The emission lines really don't look the same, even though that they are at the same redshift. This is a physical pair of quasars. And this just shows that. Zoom in on one of those emission lines, and you say, yep, those are indeed not the same. So that is definitely not a lens. So we found lots of these things. When all was said and done, we ended up with about 220 pairs. Here's a plot of a couple of them, and they're very pretty to look at. Those of you who like to look at quasar spectra like I do. Okay.
Did you have to look at?
How many spectra did we take? Oh, my goodness. We probably took a spectra of 100, some of which turned out not to be real pairs. Not every. In fact, the non-pairs turned out to be very interesting in their own right, but that's a whole other story, and all kinds of other cool things. But let's see what we did. We looked at the 2-point correlation function now on small scales, and now, by the way, we're not looking at the high redshift, and we're looking. The typical redshift of these pairs is about 1 or 1.5, something like that. Here is using different extrapolations of the large-scale correlations, just taking that parallel that one finds, and we did it 2 different ways. This the red and the green lines. And here is what we actually observed. Again, it's done in 2 slightly different ways. And you see that there's a whopping excess on small scales. We are seeing that one halo term, which is really strong. It says it's in fact appreciably stronger. In fact, remember, this is a logarithmic scale. This is a factor of 10. This is a whopping signal. Quasars really do like to sit in the same halos, which is telling something which we don't quite understand yet about how close pairs of quasars seem to trigger each other. And so one of the questions that we're in the process of asking ourselves, we're going a little slowly on this, is to look at some of these pairs and ask if they exist in particularly rich environments. If there's 2 quasars in that halo, maybe there's a whole lot of galaxies too. Maybe there's a whole cluster there. And so here's one case. There's one quasar. The other quasar turns out to be over here. There's a little cluster of galaxies around this one. Yes?
Is this the same as what you expect on one halo, or is it stronger than one halo?
It's quite a bit stronger than what you find in the galaxies. For galaxies, the effect is at the few tenths of %. Here we're finding an order of magnitude. So it's quite a bit stronger than one finds for galaxies in that. No, I don't think you. We have not tried to model this in detail, and we really should. But I think rather than using that kind of language, one really wants to think about sort of quasar triggering. Remember, we're not measuring the small-scale clustering of black holes. We're measuring the small-scale clustering of things that are actively forming those quasars, the materials falling into the quasars. We're really looking at some sort of triggering mechanism that's going on. And indeed, one of the things we're trying to do is now push that same exercise to high redshift. I spent the first half of this talk trying to convince you that high redshift was really fun, and indeed, we got to go find those pairs. And the numbers are small. The high redshift quasars are rare, and so the pairs of high redshift quasars are even rarer. But here's a particularly dramatic example. Redshift 3.83, separated by about 7 arc seconds, which is less than 100 kiloparsecs. Here's the spectra of these 2. Again, this isn't a lens, but the redshifts are clearly the same. Okay, so what I want to do now is switch topics. I've gotten past the first bullet on my list of things to cover. I told you I wouldn't finish everything I have. And I want to talk, the discussion thus far has been, again, in the context of the SDSS, what might call a classical quasar, optically luminous, very blue objects with their broad emission lines and all that. But for a long time, those X-ray astronomers and infrared astronomers have been giving us optical astronomers a really hard time and saying, come on, you guys don't know anything about quasars. Everyone knows, if they look at the X-ray surveys and the infrared surveys, that your typical quasar is not one of these blue things with broad emission lines, but rather an obscured object. And look at our beautiful Chandra surveys and our Spitzer surveys. There's loads of these AGN that you guys are not even finding in your surveys. So we got sort of, after hearing this just once too often, we decided we had to do something about that and go out and show them, but we know how to find obscured quasars as well. So in fact, indeed, optical astronomers have known this for a long time. What we call Seyfert galaxies, which is an old-fashioned way to say low luminosity quasar, we know that they come in two types. Astronomers love to divide things into types, type 1 and type 2. Whenever possible, we divide them up. And so what is a Seyfert 2 galaxy? Here's a spectrum of a typical Seyfert 2. It shows a galaxy continuum. There's starlight under there. And strong, narrow emission lines, which with line ratios that really can't be explained by star formation. So the interpretation is that there is a central quasar giving off a very non-stellar continuum, very X-ray luminous continuum that's exciting gas that you see as these narrow emission lines. But we don't see in addition the continuum itself. It doesn't show up in the X-rays. It doesn't show up in the optical. And the explanation, which I think I have here, here's the standard cartoon, is that there's this central black hole and there's the accretion disk where all this high energy stuff is going on. There's a obscuring torus of dust that hides our line of sight directly from this stuff. That is, this is obscured to our line of sight. We can't see the very high energy continuum and the broad emission lines coming from the central region directly in these objects. However, this dust does not cover full 4 pi steradians around this object. And so gas that's here and or here is getting illuminated by this and getting excited by that. And this is outside of the region that the dust is obscuring. We can see that directly. Okay? And so the interpretation then is, yes, there is a central AGN in here. We don't see it directly, but we sure do see the gas that's excited by that, far enough away from the central black hole that's not deep in the potential well, and therefore has narrow emission lines, not broadened by the very large Doppler effects one gets very close in. So the optical astronomy community have known about these for a long time. And so the name of our game here is to ask the question, do we find analogous objects not at the relatively low wimpy luminosities that one finds that the Seyfert 2 galaxies are, but can we find what we'll call type 2 quasars? Do high luminosity analogs of a Seyfert 2 galaxy actually exist? So what would be their characteristics? We'd see very little quasar light in a continuum sense. We see very strong, narrow, high ionization emission lines, those things that are excited by a quasar continuum. And so off we went to go find these things. And Nadia Sakamska finished her thesis a few years ago to go look for these. And it's been lots of fun. And indeed, lo and behold, they exist. And so these just are basically examples of those Seyfert 2 galaxies that I showed before, except on steroids. The emission lines are just off-scale strong. The underlying galaxy is so wimpy compared to all this that you can basically barely detect it. These are almost, not quite, but almost continuum-free. And these huge whopping emission lines, but no broad emission lines like you find in ordinary quasars. And here they are. And those of you who love the arcana of obscure emission lines can go through and identify all kinds of ionization things like there's, singly ionized helium, which you only get in sort of extreme environments. And there's some high ionization neon lines out there that will show up. Okay, so you look at these things and say, well, this is just what we're looking for. We're happy. Can we prove that these indeed are obscured? Is there really a quasar in there? I've told you a story here, and I just said I sort of made it optimal for myself by saying, these things show up by not showing the quasar activity, and therefore there's a quasar. Saying, well, that's not the most convincing argument in the world. So how do we make that more convincing? Well, one way we do so is to go back to this picture and recognize that in addition to the central engine causing this gas to fluoresce, which is what causes the emission line, there's actually going to be just some old-fashioned scattering off of either dust or electrons up here. And any scattered light from that central engine that comes here will be strongly polarized. And so the prediction is that the weak continuum that one finds here will indeed be strongly polarized. Moreover, the spectrum of that polarized light should be that of an ordinary quasar. And so we went out to do exactly that. And lo and behold, here's one specific example. And let's see, there are many panels here. Here's the original spectrum of this thing, whopping emission lines of all kinds. This is the same spectrum. And here is the spectrum of the polarized flux. Now what we see is that the strong emission lines go away because the emission lines are coming from a much larger region. They're not scattered light. They're not polarized. The strong emission lines have gone away. You see a very blue continuum, and you do see some emission lines. You see some broad emission lines which come. This is basically the broad line region of the quasar reflected off of what we're seeing. So lo and behold, these things really are, and another thing is that the polarization fraction is whopping. These are almost 20% polarized. In the polarized spectropolarimetry game, people get real excited when they're over 3%. This is 20%. So these are big numbers. These are really strongly, as strongly polarized as any extragalactic object I know of in the optical. So these things really are hidden AGN. And our picture is indeed more or less correct. So we're happy. This is one example. We have a bunch more that we have measured like this. Needless to say, this is the prettiest, but that's the way, the nature of the game. I'm sorry? It's difficult, and the reason is because you do not know in detail the geometry of the stuff that's doing the scattering. You do not know how much contamination in the original spectrum is coming from the host galaxy, which will dilute things. So the quick answer is no. You can try to turn things around and try to infer the geometry. We did some of that here. One of the fun games that we played, one of the themes in this field for some time has been to go look at the host galaxies of quasars, because one wants to learn of the type of galaxies in which quasars might live, and people have been playing that game with HST for some time. Our objects are ideal for this, because here's a quasar, which we're arguing is a really luminous object, and yet we've blocked out the light from the central engine. From ordinary quasars, it's really tricky, because you're trying to find that faint host galaxy from this searchlights staring at your eyes and just dazzling you. We've already blocked that out with the dust here. And so here are pictures of three of these objects. And what you find, interestingly enough, you find these funny sort of vaguely elliptical-like things. Some of them look like they're involved in mergers. But the other thing that you find is that you find scattering cones. This is indeed found at low redshift. Again, if we come back to this picture, and then if there's scattered light coming off of here, you might actually expect to find a blob of the blue light from that central engine coming from, whoops, I'm pointing at my screen. That's not good. Coming from over here. You might expect that, as it were, this whole region is lit up. Oh, even better. Okay, I'm tied to this umbilical cord, so I'm bound to trip over myself and kill myself at some point. But okay, so we might expect, as it were, that this whole region would show up, and you might generically expect some sort of cone-like structure. And when one sees something like that, this is the structure in continuum light, not emission lines, by the way, and it's better on my screen than here, but you see a vaguely cone-like structure. In this case, it seems to be bipolar. There seems to be cones coming out in two directions. So we might imagine that a lot of that blue polarized light is basically what we're seeing in this picture here, which is kind of fun. Okay, and here's a picture of a bunch of these things. Some of these look like they're undergoing mergers and other fun things, which again, as people have been saying for some time, that quasar activity may be related to mergers. So that's an interesting game. Okay, we can try to estimate how luminous these objects might be by looking at their infrared light. After all, that energy that they're giving off has to go somewhere. It's absorbed by the dust, but it heats up the dust, and it will be re-radiated in the infrared. So here's a picture of one of these things, little wimpy-looking thing in the optical. At 3 to 8 microns, there it is. It's just booming. It's sort of the brightest, in this case, reddest object around, and as seen with Spitzer. And we can go study these. And what we're finding then is trying to get something close to a true bolometric luminosity of these objects. It's a tricky business, because the quantity one really wants to know about is just how much luminosity these things are giving off. I made the statement that these things are luminous quasars, and the obvious question is, okay, how luminous are they? Well, we can get some handle on that in the infrared, and each dot here represents the spectral energy distribution of one of these quasars. Here's what an ordinary quasar looks like, very, very roughly flat in nu L nu. These things are rising into the infrared. And indeed, we can ask what the bolometric luminosities are. These really are quasar luminosities. Here are the kind of numbers, 10 to the 44 to 10 to the 46 ergs per second. These are bona fide quasars. These are not little wimpy Seyferts by any stretch of the imagination. Okay, I'm going to skip that. And so Reina Reyes, who's a graduate student at Princeton now, and Nadia Sakamska and I then want to ask the next question, which is, okay, how common are these things? How do they compare in numbers to ordinary type 1 quasars? And remember, one of the things I should have emphasized, the sample that we're talking about, we're not pushing to terribly high redshifts. The sample goes up to about redshift 0.8 or so. We're not finding incredibly faint objects at redshift of 2 or 3. that would be cool, but at least to the depth of the SDSS, we're not going to do that. So what we did there, again, we don't get a direct measurement of the bolometric luminosity of each quasar. If someone would give us lots and lots of time with Spitzer, we'd go off and do it, but no, that's not going to happen. So, so what we use as a proxy is the strength of the strongest emission line, the 035007 line. Let's see if I can have a spectrum. That's this whopping line right there, which has been suggested with some hand waving as the best thing you can use as a measure of the luminosity of the quasar, given that everything else is obscured away, at least in the optical spectrum. And so what we did was measure the luminosity function of that emission line and compare it with the luminosity function of ordinary type 1 unobscured quasars at the same redshift, as also measured in that emission line. We did this in 3 redshift bins. And let's see what's going on here. Red here is the type 1 quasars, the ordinary quasars, and there's actually 2 versions of blue and black, various corrections that we tried to do, but these are the type 2 quasars. And what you want to see is that at the highest luminosities, at least, the 2 populations are actually quite similar in number. At lower luminosities, there's all kinds of incompletenesses, which we do our damnedest to try to correct for, but we know we're not doing a good job here. But the highest luminosities, the two populations seem to be actually similar in number. That is, obscured and unobscured quasars at the highest luminosities are roughly equal in number over the redshifts that we're looking at. I'm sorry, not sure I understand. No. We can measure the oxygen narrow line luminosity for both samples of quasars. We can play that game for each. It's a narrow line. It's narrow line nominally unobscured luminosity in each object. That's the comparison that we make. So here is a fraction, the fraction of objects that we find in our sample. These various lower limits. Every point you'll notice is indicated as a lower limit because there's a whole we go for several pages in our paper listing all the senses in which our sample is incomplete for all kinds of reasons, and so we plot every single point as a lower limit, and you can see that it's 30 to 50% depending on exactly how one slices things. That is, unobscured. These obscured quasars are really quite common even at the highest luminosities, and that so if one is doing quasar demographics, one really has to worry about these relative numbers. So I have gotten through about half my talk, and I've run out of time, but this is actually not a bad place to break. So let me just tell you what I would have talked about if I had more time. I would have told you all about how to actually get something about the masses of the black holes which are powering all these things, and how careful you have to be to do all that kind of stuff. And then I would have gone on to, beyond the concluding thoughts, talk about high redshift quasars, which I already knew I wasn't going to be there. So what have we learned about? We've talked about how studies of the clusterings of physical properties and the demographics of quasars, including the obscured populations, really require massive surveys. SDSS, we've really found ourselves, despite this being the biggest survey around, is really barely big enough to really do the analyses properly. We'd love to go to fainter magnitudes to go find out what quasar clustering does as you go lower in luminosity. We'd love to push to higher redshifts in these obscured quasar populations and go find out what's going on there. And we are very much limited in our ability to do such things by size of the SDSS. We started out saying, can't imagine anything bigger than this, and already we're complaining this is just the way it is. Understanding quasars in the host galaxies. Well, this was in the context of trying to understand their host halos in particular. It still needs further exploration at higher redshift, especially for the lowest luminosity AGN. And again, we are limited in dynamic range. We at any given redshift, the SDSS probes only sort of the most luminous objects. And so one of the things that we need to do for the future is go push to lower luminosity objects where the models really start making rather disparate predictions about what the nature of these quasars are. And that's really what future surveys will be all about. So I will finish there. Thank you.
What fraction of the type 2 objects that you looked at polarized light do not show broad lines?
So I was told I was supposed to repeat the question for my device here. So the question was, what fraction of type 2 quasars with spectropolarimetry measurements don't show the broad lines? I think we've done this for a dozen such objects, and for those, only a few have the signal-to-noise ratio to really allow us to make statements one way or the other. And for those few, they all show broad lines. But that's not a very impressive statement. Again, these objects have a continuum magnitudes of about 19th or 20th, and so getting spectral and the polarization fractions. I showed you one that was 20%, but a more common number is a little less than 10 or 5%. And so really doing real spectropolarimetry to be able to measure a broad line requires some serious signal to noise, which we haven't done enough to give proper statistics of that.
What if you use X-rays to select type 2?
People have done that. And indeed, one of the things that we can do that the X-ray and, for example, the infrared surveys can't do, we have the solid angle. And what that gives us is to give us the relatively rare highest luminosity objects. The X-ray surveys are limited to, by their nature, to a small number of square degrees. And so the number of really luminous objects that you expect in there, they being rare, is going to be relatively small. And so they don't have the statistics to really address these questions at the highest luminosities. There are hints from the X-ray literature that the ratio of obscured to unobscured objects drops as you go to higher luminosities. Again, we're a little limited in dynamic range, which I was just complaining about. So we really can't. I showed you a plot that showed things as a function of luminosity, but again, you may remember that everything was lower limits. So we really can't say very much. These gray points I didn't say are mostly from the X-ray studies, in fact, and they do mostly at higher redshifts. So it's not directly comparable, but they say basically everything's obscured at low luminosities, and as you go to high luminosities, the numbers drop. We don't have really the dynamic range to go to lower luminosities to really say that properly. So again, 10 to the, for this exercise, about 10 to the 44 to 10 to the 46. We can go, I didn't say that quite right. At the lowest redshifts, we can just go back to the SDSS galaxy sample and study the luminosity function of Seyfert 1 and Seyfert 2 galaxies. And in fact, there we find, at about this luminosity, that about 2/3 of them are type 2s. So, we would put a data point. We should have done that. Maybe the paper's not accepted yet. We can still do it. Maybe we should put in a point here, making that point. Well, it's an interesting question because at least what I've been talking about really wants spectra. And everyone is, including stuff that I'm involved in, everyone's talking about the next generation of imaging surveys, and we hear about Pan-STARRS and LSST and the Dark Energy Survey and Sky Mapper, and I'm sure I could rattle off a few more off the top of my head. Relatively few people are talking about large, massive spectroscopic surveys pushing to fainter magnitudes. And, as you know, what was it? A spectrum is worth 1,000 pictures or something like that. There's an awful lot that one gets. You can do some of this stuff. For example, the high redshift quasar clustering stuff. You can imagine doing that photometrically because quasars, as I tried to say earlier, quasars really do stand out photometrically. High redshift quasars stand out photometrically. Moreover, you can actually do a pretty good photometric redshift of a quasar from its colors because as you go to high redshift, there's a very strong break across the Lyman alpha. You get two breaks actually. One from Lyman alpha to the Lyman alpha to the continuum, suppressed continuum from the Lyman alpha forest, and then a second break at the Lyman limit at 912 angstroms. And those two breaks then allow you to do quite good photometric redshifts if you have good photometry to an accuracy of about 0.2. So one can imagine doing a photometric survey of high redshift quasars, again above redshift 3 or so, and with those then measure clustering. And I have not gone through those numbers in detail to figure out what the next generation of surveys should do, but that's a good exercise to carry out. Adept and so on. Yes. They should, but they are. They're working at quite low resolution and are really interested in getting a redshift only, and therefore will not have a lot of detailed spectral diagnostics. Redshift only already gets you a fair way. I'm not, comparing, once you know the redshift and if you have the photometry, you can figure out what's a quasar and what's a galaxy. So that'll be a useful thing to do. Well, let's see, what was I going to say? To do interesting detailed spectral diagnostics, like looking for those type 2 quasars, for example, that really requires, fairly moderately high quality spectra at reasonable resolution, which those surveys that you're making reference to are not going to be able to do. So those surveys at the moment are very focused on dark energy. Wonderful though dark energy is, there's other things. Well, it's going to be a difficult game. SDSS sort of found a perfect niche where you could get spectra of large number of objects at high quality. If everyone would love to go do, say, as it were, galaxy properties at redshift 1 or redshift 2. Those objects are seriously faint, and the Keck telescope did the deep survey, and their spectra are not at the level of quality here because they just have far fewer photons to work with, and so it becomes an increasingly very difficult game to play.